computer. Well, good afternoon and good evening and good morning for the rest of the world. My name is Wenming Yi. I'm a program manager or product manager on AWS AI. So part of what I do is I work with the DGL team. That's one of the frameworks that I'm helping with. And we have been running this, I would say, workshop or user group meeting for quite a while now. And we would love to have you spread the words. And if you can, definitely have folks to join our Slack channel. And I'll post that in the YouTube channel, and I'll put a link there. So folks are very welcome to join through the Slack channel. And the Slack channel has grown to about 1,300 people. So we definitely see a lot of user activities there. So thank you for the participation there. And today, I think we have a shortened meeting. The reason is because it's a holiday in the US. It's the Memorial Day weekend. So I think a lot of people may even have started their weekend, long weekend early. So happy Memorial Day. And then we have only one speaker, so I've shortened the meeting a bit. And this is Hong Kwan. He's already here. He's going to talk to us about something fairly interesting. It's a general framework for temporal GNN training. And I think you are actually currently interning at AWS. Is that right?
Yes, I'm a return intern this summer.
That's great. Fantastic. Well, welcome back. And I'll just hand that over to you.
All right. Thank you for the introduction. And let me first share my screen. Can you guys see the slide?
Yes, it works.
Okay, so hello everyone. Nice to meet you all. And I'm Hong Kwan Zhou. I'm a third-year PhD student under the supervision of Professor Prasanna at USC. And today I'm going to introduce the work that I did last summer as an intern in the DGL team together with my colleague Da, Israt, Vasilios, Xiang, and George. So the title is called TGR General Framework for Temporal Graph Training on Billion Scale Graphs. And this paper is going to appear at this year's VLD. So I'm going to arrange today's presentation as follows. So first of all, I'm going to start with the motivation and challenge of the designing a general framework for temporal graph neural networks. And then I'm going to give a very brief and high-level introduction on different approaches to the temporal GNNs. And then after that, I'm going to introduce the proposed framework TGL, followed by some experiment results and conclusion future works. So let's first start with the motivation. So the motivation is actually quite simple. We all know that compared with a static GNN, the temporal GNN can capture the additional but very important temporal information as well as the contextual and the graph information. And this additional temporal information have proven to be very useful in many real-world applications. However, on one hand, these existing temporal GNN models, first of all, they have basically unique data set and configuration format. So it's very hard to apply a data set or apply different configurations to different models. And secondly, because sometimes they are proposed to solve some specific problem in a specific domain, so that it might usually it might not compare with the others on a general data set. And lastly, they're usually evaluated on a small scale data set. And also because it's small scale data set, so there's not really necessary for a multiple GPU machine. So it's also trained on a single GPU. On the other hand, currently we have one temporal GNN framework that is called the PyTorch Geometric Temporal. However, this framework is limited to the snapshot-based method only on the discrete time temporal graph. And it also only supports full batch training, so it's very hard to apply it to a large-scale data set. So the motivation is quite clear. We need something that is general and efficient for the temporal GNN training on the dynamic graphs. However, in designing this, designing such a framework is quite challenging. So first of all, how should it look like so that it can support these various models which actually behave quite differently? And secondly, we have some efficient static temporal samplers, but on a temporal graph, when you do the sampling process, you want to consider the timestamp of different graph events and how can we efficiently do this. And thirdly, how can we train on a large graph with multiple GPUs? And also there's another question because there's currently not a large-scale data set on the market really. So the last challenge is that we need to find some large-scale temporal graph data set that is good to evaluate the performance of various models. Well, next I'm going to introduce some basic of the temporal graph neural networks, and I'm going to talk about the 3 basic building blocks that most TGN models, they use this basic building block as their common components to compose their architecture. So the first building block is called the node memory. So it basically summarizes the past node states. So the reason we want to have a node memory is that sometimes your graph time span of the graph is really long, and it's very hard to directly sample some neighbors and know what's happening in the past. So that some model introduced this node memory to summarize the states of the nodes in the past. And node memory is usually updated by the messages, or we can also call it mails of some corresponding events. So in summary, this SV could be, we denote SV as the node memory. And there is an update function which takes the original SV and a combined message of all the corresponding graph events in the current mini batch. And for example, in the popular TGN model, this update function is GRU cell, and this combination function simply take the most recent messages. And also in TGN, the message looks like this. So it's a concatenation of 4 parts. So the first part is the node memory of the source node. And the second part is the node memory of the destination nodes. And the third part is a time feature. And the last part is the static edge feature. Note that sometimes some models define the corresponding events not only as the event that's happening at a destination or source node. Sometimes this mail is delivered to the neighbors. For example, the APN model actually deliver the mails to the hop 1 neighbors. And the second building block is called the attention aggregator. So it's similar like it looks very similar like the transformer attention aggregator in the NLP models, and especially that it has this query key and values. But the only difference is that the position vector is replaced with this time encoding vector. So this phi 0 is time encoding that map point time or time duration to a vector. And the last building block is of course, the temporal neighbor sampler. So it's observed that this temporal neighbor sampler either samples past neighbors uniformly or samples the most recent neighbors, depending on what neighbor information you want to get from the model. And also, it's used both in the attention aggregator as well as the node memory, because as I mentioned before, some method actually needs to identify the destination of the nodes so that they can deliver the mails or the messages to some farther nodes. And based on these 3 basic building blocks, we can actually build a lot of different types of temporal GNN models. For example, by only using the attention aggregator, we can build TGAT, which is act very similarly as GraphSage, but have these additional temporal encodings or the time encodings, and so that it can capture the time information. And by using this node memory building block, we can build Jody, DIRAP, or APN, which directly use the updated node memory as the dynamic node embedding. And also we can combine these basic building blocks. For example, if we combine the attention aggregator plus the snapshot strategy, where we divide the graph stream into different snapshots according to time and apply this attention aggregator within each independent snapshot, and then finally use a combine function to combine the information from multiple snapshots and generate the output dynamic embeddings. We can build different methods like evolve, GCN, and dataset. And lastly, if we combine the node memory and the attention aggregator together, where your node memory basically serve as the static feature or similar to the static feature in a static GN, and which provide input data to the attention aggregator, we have the famous TGN model. So in this work, we support various temporal GNNs by providing efficient implementation of these three components. Okay, so before I start the framework overview, are there any questions? Okay, so let's go ahead and look at the overview of the TGR framework. So in this left figure, we can see that TGR actually have 5 main components: the sampler, the mailbox that stores the messages or the mails, the node memory, the memory updater, and the attention aggregator. And the left part for the memory, mailbox, and sampler is usually stored on the CPU because it contains information of the whole graph. But sometimes if your graph is not large, and this whole thing could be stored on GPU, it could also be stored on the GPU to eliminate the overhead of slicing and copy the data from CPU to GPU. And the general model follow the following training path or the following computation path. So firstly, you get some timestamp nodes where you want to get the dynamic node information of these target nodes. So we first do a sampling using our temporal parallel sampler to get its temporal neighbors. And then this sample data is sent to the mailbox to look up the memory as well as the mails to update the memory. And then they are sent to the memory updater, which is basically a neural network on GPU, and the memory is updated there. And after that, the updated memory is sent to the attention aggregator to compute the final dynamic embeddings, and we do a backward propagation to update the learnable weights in the memory updater and the attention aggregator. At the meantime, after the memory is updated, we can use this updated memory to update the global copy of the node memory as well as the mailbox. So note that there are some models that doesn't use all of these modules. For example, for those TGAT and Datasets or something like that, that doesn't have a node memory, so it basically don't need the mailbox memory and the memory updater part. So let's first talk about the temporal parallel sampler in TGR. So we first observe the common properties of temporal neighbor samplers in different temporal graph neural networks. And we can summarize 3 common points. So firstly, they all samples within the graph snapshot. And for the method that doesn't have a graph snapshot, we can actually view it as a snapshot that contains all the nodes or all the graph events. So it can be viewed as one whole snapshot. And secondly, it all samples neighbors either uniformly in time or the most recent neighbors, depending on what the model chooses. And lastly, it operates on the target node that come in the chronological order, which means that you always train on the graph events that are before in time than the graph events that are later than you train graph events. So the question or the key point to design an efficient temporal parallel sampler is how can we quickly identify the candidate edges to sample from? So we check the open source code of most existing works, and we see that usually a lot of time is wasted when they are trying to create these candidate edges, and it usually involves a lot of memory copies. So basically, they extract the graph up to some timestamp and make a copy from the original whole graph and try to sample from that, and that creates a lot of overhead. And our solution to that is called the temporal CSR or the TCSR data structure. So similar to the original CSR data structure, we have a indices pointer array that stores the indices of each node. And we also have an indices array that store the neighbors of each node. Note that here, these neighbors are defined as temporal neighbors, so that if one node have multiple interaction with another node, there will be multiple entries in this indices array. And in addition, we add this timestamp array, which stores the timestamp of these graph events. And in this timestamp array, we also sorted the neighbors according to the times, so that the prior events are strictly has lower address than the later events. And by doing so, actually we can use this pointer array to mark the start and the end of a dynamic snapshot. For example, in this figure, we show a snapshot. We show a status of two snapshot sampling, a two snapshot sampler. So there are two snapshots S1 and S0 on the graph, and we have 3 pointers that indicates the beginning and the ending of this snapshot, so that we only need to move these pointers when we during the training process, and when we want to identify the candidate edges, it will directly tell us what is the range of the candidates edges that is in the indices and the time array. And the space complexity is 2 plus the number of snapshots times the total nodes in the graph plus 3 times the number of edges, which is only, so we only have an additional time array as well as this point array, which is in the order of OV. And in most temporal graphs, we have far more edges than the nodes, so that the extra space complexity is acceptable. And this is the algorithm that shows the our temporal parallel sampler. So we samples from the layer that is closest to your target nodes to the layer that is farthest to your target node. So we first get the target node that we want to sample, and then we advance the pointer of these end nodes to its correct place. And this process is done in parallel, but note that when we advance these pointers, multiple threads will create a race condition, because sometimes they might be it might be possible that they want to increase the pointer or advance the pointer at the same time, which creates the race condition. So to solve this issue, we add a node-wise lock to avoid the race condition. And also in a multiple hop neighbor sampling algorithm, if they are using the timestamp, if they are not using the timestamps of the root node during the sample, that is that when you sample your hop 2 neighbors, if you use the timestamp of your hop 1 neighbors instead of the timestamp of yourself, then for the second layer or the later layer, we actually cannot use this pointer array. But thankfully, our TCSR data structure has a sorted timestamp, so that we can still use a binary search to quickly find the candidate edge site within O log n complexity. And then let's talk about the multiple GPU training part. So we know that these temporal GNNs are very similar to a static GNN. They are not very large models. So it's very hard to leverage the model parallelism. And also these node memory-based models, they cause this intrinsic data dependency in the global copy of the node memory. So we decide to go with the synchronized multi-GPU on a single node setup that best fit the need of the TGR. So to train a TGR on n GPUs on a single node, we first launch n trainer process and one sample process. The sample process will first sample n local mini batches, and these mini batches would be scattered to the n trainer process through the glue backend. And then the trainer process would slice the required node and edge feature, node memory, as well as the mailbox. So these things are stored in the shared memory, which is shared across the different processes. And then the trainer process will perform the forward and backward computation and sync the model in the NCCR backend. So that's purely done on GPU. And then after the memory is updated, they will update the node memory and mailbox, which is stored in the shared memory again, and repeat this step until the training is done. However, in this multiple GPU training, there is actually a problem, because the more GPU we have, the more global batch size that we'll be using. And actually, for the node memory-based TGNs, you don't want to have a very large global batch size. If we divide the temporal dependencies into two types, the intra-dependency and the interdependency, we can see that the intra-dependency, which refers to the node dependency within one mini batch. So this part, because one mini batch have to be computed in parallel, so that all of these intra-dependencies are discarded during the training. But for the interdependency, that is actually the temporal dependency that the model is learned during the training process. And it is actually the node dependency between different mini batches. So here is the problem. If we have a larger global batch size, we will have more intradependency that is discarded due to the large batch size. And we will have less interdependency, which is captured in the model, so that it will lead to a lower accuracy. So our goal is to allow the model to learn more dependencies with large batch size. And our solution is called the random chunk scheduling algorithm. So the solution is basically, since with a large batch size, we cannot capture all the, we cannot capture a lot of dependencies in one epoch. So we turn to capture the dependencies, we turn to capture as much dependencies as we can, but in multiple epochs. So the idea is that we divide the input edge stream into fixed size chunks, and we allocate the mini batch starting with random chunk in each epoch, so that the model could learn more relationships with within multiple epochs. So in this figure, the nodes or the edges, they can be either thing is the same. So if they are in the same color, it means that they are in the same mini batch. And if they have if one square has the same pattern, it means that there is a dependency. And we can see that if we have batch size equal to 3, under the normal scheduling, we will always train under this batch size or under this mini batch scheduling, which means that we can only capture this dependency with between this red batch and the green batch. However, if we set the chunk size equal to 1 and divide it into 3 chunks, within 3 mini batch, the first mini batch can capture 2 dependencies, while the second can capture 3 dependencies, and the last one can capture 1 dependency, which means that within 3 epoch, we are still able to at least feed all these temporal dependencies to the model to learn. And this is the user interface of TGR. So I just show 4 examples, example model, the configuration file for example models. And it basically has 4 parts. So the sampling part, which specify what is the sampling hyperparameters you want to use. And it also specify whether you want to use a snapshot during the sampling. And then the node memory the memory part specify the parameters in the node memory, and the GN part specify what is your architecture in the GN. And the last one is just some common training hyperparameters like the batch size, the learning rate, the dropout, etc. And we evaluate the performance of TGR with 5 baseline methods. So we have Jody from KDE19, we have Dataset from WSDM20, we have TJT from iClear20, and we also have TGN from ICML20 workshop. And the latest model we use is the APN from SigBoy21. And besides the 2 existing small-scale dataset, which has less than 1 million edges, we also propose 2 large-scale datasets that aim to test the ability of different TGNs to capture information in 2 different dimensions. And the GDL dataset has around 200 million edges, while the MAG dataset has 1.3 billion edges. So for the GDL dataset, it originates from the GDL project in Google, and it focuses on capturing the multiple node information with dense temporal interactions, because we can see that only 17,000 nodes has around 200 million edges. So it's actually very highly interactive dynamic graph, and it records the worldwide events happening from 2016 to 2020 with a time granularity of 15 minutes. And the link prediction task is to predict whether there will be an event between the 2 actors. So here actor doesn't necessarily mean actors, but it can also be like country, people, or other things. And the node classification task aim to predict the location, or specifically the country, of a generally defined actor when one event happens. And the second data set is the MAG data set. It originates from the MAG 240 million LSC data set in the OGB LSC data challenge. And it focuses on testing the performance of TGN on large graph with stable nodes and edges. So it's a citation graph, so that once an edge appears, and also once a node appears, it tends to have more like static history or more static representation. And it records the citations from within 120 years with a time granularity of 1 year. And the link prediction task is to predict if one paper would cite another paper, while the node classification task is to predict the primary subject of that paper. So let's first look at the result of the temporal sampler in TGR. So we evaluate on G4DN.8x large AWS instance with 32 virtual CPUs and 128 gigabytes of memory. And we test 3 typical sampling algorithms, including the snapshot and uniform sampling algorithm that are both 2-layer, and the most recent sampling algorithm that TGN use, which is a 1-layer sampler. And we can see that by using 16 threads, we get around 2 to 3 times speed up, while the speed up furtherly boosts up to 4 times when we switch to 32 threads. So this is due to the extra L3 cache from the other NUMA node. And if we look at the runtime breakdown, we can see that the scalability of the time spent in maintaining these pointer arrays doesn't scale very well, because we have this cross node, or we have this cross node, what is that called? Cross node a lock. I'm sorry, it's a lock. And time spent in binary search actually scale very good. And the last gray bar is the time spent to combine this. Combine the sampling result from different threads. So the workload size grow with the number of threads, so it also doesn't scale very well. And compared with the open source baselines, our sampling time is anywhere between 57 to around 300 times speed up when using 32 threads. And then let's look at the single GPU performance on the small scale dataset. So these are evaluated on the same instance on a T4 GPU. And we can see that TGR achieves similar or higher accuracy compared with the baseline method on all 5 methods. And however, the training time of TGR is significantly faster with an average of 13 times speed up. And if we look at the performance, we can see that on the Wikipedia and the Reddit dataset, both TGN performed the best, while Jody and TGAT performed the second best, while Jody and APN, due to their very simple pure memory-based model, they have the fastest runtime. And here is the convergence curve of the validation AP and the training time of these 5 different models. And we can see that TGN Datasets and Jody has the fastest converge rate, while TGAT and APN has a relatively slower convergence rate. And again, TGN has the highest accuracy. And from the runtime breakdown, we can see the right part is the sampling part. So due to our efficient temporal parallel sampler, the sampling overhead is actually very small. And most time is spent in the computation part on GPU, especially for the 2-layer model due to the neighbor explosion problem. So lastly, for the, I'm sorry. And then let's look at the performance of the random chunk scheduling algorithm. So we plot the validation loss with respect to the number of epoch under different batch size. So the first number is the batch size. So the dotted line shows the batch size of 600, which is used as a reference line. And the black line shows the vanilla training of batch size equal to 4,800. And without this random chunk scaling algorithm, and these two red lines shows the convergence curve with random chunk with chunk size 16 or 32, and we can see that if we enlarge the batch size, it actually performed quite worse compared with the reference convergence. But if we enable this random chunk scaling algorithm, we can see that larger batch size can achieve very similar performance than the smaller batch size. Also consider a case that when you enlarge the batch size, it usually trains faster due to the data parallelism on GPU, and which means that you can actually speed up the whole convergence process. And note that on the too large version of the dataset, we noticed that in experiment, we noticed that the largest batch size available on the 32 GB GPU, which is 4,000, it actually already performed quite well without this technique. So we actually didn't use it in the experiments of the large graph. For multi-GPU on large-scale dataset, we evaluate the performance on a P3DN.24x large instance with 8 NVIDIA V100 GPUs. So each GPU has 32 GB of main memory. And we don't have a baseline result because all the open source code, they cannot run on such large dataset. And we can see that on the GDLET dataset with around 200 million edges and 20,000 edges, TGN and APN as well as Jody can finish the training within 1 hour, while Datasets and TGAT needs more than 3 hours to run 1 epoch. Note that here TGN also achieved the highest accuracy on the 2 large-scale datasets. And on the MAG dataset with 1.3 billion edges, the fastest method, Jody, still needs more than 1 hour, and TGN needs around 3 hours, while Datasets and TGAT basically needs more than 10 hours or around 10 hours for 1 epoch of training. And APN cannot be run on MAG because it requires the mailbox to store 10 most recent mails, and that is simply out of the memory of the 1 terabyte memory on the EC2 instance. And we can see that the normalized runtime or the training time per epoch when we use different number of GPUs on the GDLET dataset is that we get an average of 2 to 4 times speed up on the on 4 GPUs and hardly any further speed up on 8 GPUs. And this non-linear scalability is mainly due to, firstly, is the communication bottleneck between the CPU and GPU, and secondly is the synchronization overhead on the node memory. So in conclusion, in this work, we propose this general TGN framework that can express most mainstream temporal GN models by simply writing some YAML configurations. And secondly, we designed this special TCSR data structure for dynamic graphs, as well as an efficient parallel sampler. Lastly, we propose these 2 large-scale datasets that focus on the testing the capability of models in 2 different dimensions. And the TGL is available at this GitHub link, as well as the 2 large-scale datasets. And as Wenmi mentioned, I'm doing an internship again at the DGL team this year. So I'm currently working on improving the scalability of the memory-based TGNs on multiple GPUs, as well as distributed GPU clusters. So I think that's all of the presentation. Are there any questions?
Yeah, thank you, Hong Kong. I'll let people ask questions.
Hello, this is Tristan from NVIDIA. Thanks for the presentation. It's very nice.
Thank you.
Somehow, yeah, we didn't have much attendance like last time, but it's great presentation. Is this based on the DGL 0.6? I wonder when you do the performance.
I think it's 0.7 or 0.6, yes, but I think I majorly only use the MFGs concept in DGL, and the other things are all written by PyTorch. So I think it should be compatible with many versions of the DGL.
Right. And the reason why I ask, I wonder like whether the training time is actually the training the model forward backward, or it's actually the data pipelines, because the usually data loading and sampling takes quite a lot of time.
Yeah. So in this runtime breakdown, the red part is the sampling overhead, and the blue part is the data loading, including the slicing and also transfer. And the green part is the computation that is done on GPU. And I think on a single GPU, the dominant time, at least for this 2-layer model or this complex model, if we call it a complex model, is the dominant time is still the training time on GPU. But on multiple GPUs, the dominant time should be the synchronization cost, as well as the feature slicing cost between CPU and GPU.
Thanks. Another question for the batch size, you mentioned like you jump from like 600 to 4,800, right?
Yeah.
Is like general conclusion that there's maybe a optimum batch size to train these models, or could be changed by different optimizer?
I think not necessarily there is like a best batch size. I think as long as it's small enough, it should be enough, because for these memory-based models, you only update the node memory once for each mini batch. So if you have larger mini batch size, then you are going to update the memory less frequently, which means that your memory will be out of date, or it will be very stalled. So the reason that it favors small batch size is only that it wants the node memory to be updated frequently, so that more dependencies could be captured during the training.
Right, because on these 2 graphs, like it's very interesting because on your Reddit data sets, the smaller batch size overfeed way later, while the large batch size over. If you can pull out a little bit more, for your 600 batch size, I want to like see where is overfit, right? Because for your 4,800 batch size, no matter it's like 16 random chunk or 32 random chunk, it actually looks like overfitting at 20 epochs.
Yeah, I think if I remember correctly, this is not actually overfit. It's just the batch size is too large, so it cannot capture the multiple features in the graph. If I remember correctly, this is not overfit. So the training loss is at least, if not similar, but it's still not like going down after.
Oh, okay. Yeah, it would be nice, like show you this the training accuracies here. That'd be nice. All right, thanks.
Sure. I think if you're interested, you can ping me and I can let you know the data.
Yeah, sure.
Also,
thanks.
you can try it yourself. It's from Nicole.
Yep. Thank you.
Yeah, also, Hongkai, if you can share your slides on the Slack channel and the general channel, that would be great.
Yeah, sure.
Yeah. And also,
yeah, there's a lot of like useless stuff. Let me prove that, and I will show the. I will share a clean version.
And also, do you have a link to the actual paper on the?
Yes.
It is okay. It is on the actual PowerPoint. Okay, that's fine.
I can send the archive link.
Yeah, it's great. Yeah, so if you can, I think just put it on the Slack channel.
Oh yeah, sure.
Yeah. So anyone else has any questions?
Yeah, I guess Leo from Graphistry. So, and this might also I see like, so I don't know if like Tristan and others from the NVIDIA team, like what we're thinking about is a couple of scenarios, like some are bigger than memory and some are like probably could fit in memory. And so our normal pipeline would be something like, whether we're taking like a gigabyte of Parquet or like, a terabyte of Parquet, like whatever. Often we might actually be feature rich. So maybe we've like had to factorize some text or a lot of metadata, think a lot of event data, not just time series data. And so what I'm wondering in these cases, like in general, we're pushing more towards like, cuGraph and Dask cuDF versus just Dask. And so just could we keep it all on GPU? And you talked a little bit about there. And so I'm kind of curious about what you're seeing there with potentially wider data and then also potentially just end-to-end GPU, like whether like what your experience is so far and just looking ahead as you guys work with the cuGraph team.
I think for me, yes, so for this year's internship, I'm working on, or I'm at least thinking of trying to keep the everything on GPU for a large, even for a large graph, so that the node memory could be maybe partitioned and stored in each GPU. But I haven't looked at the framework that you mentioned. It's called cuGraph.
It's cuGraph. It's NVIDIA software library.
Oh yeah. I think I'm interested in doing that, and I think that would greatly improve the performance by cutting a lot of the overhead. And I think I'll have a look at that.
Yeah, it's already integrated with DGL, so certainly just ask Da and Dominic on the NVIDIA side to if you have any questions.
Sure.
Yeah, and then this is a little more exploratory, but we're finding that they're just interesting. Like it kind of you alluded also a bit to this, that they're just like when we're doing the sampling, that I think you talked about things about like looking at like, are we doing distinct neighborhoods? Are we waiting to more like some recency thing? But we're finding like other scenarios that like there might be like dense, like something like certain, like for parts of the graph, it might be like, imagine like social network, like some accounts might be like sparse, like what kind of bursty behavior, things like that.
Right.
I don't know, like I didn't get a good look at the variety of samplers, but I was curious if you could talk a little bit about that, just like the variety of samplers.
Okay, I think so for the memory-based models, I think most of these models, they're good with the most recent neighbors. And the reason is that because you have this additional node memory and it will summarize what happens in the past, so that you are only interested in looking at the details of the things that really happens very recently. But for the other memories, for the other model that don't use node memory, typically they want to sample they typically want to sample the neighbors uniformly in time, so that if you have a very highly interactive node that has a lot of neighbors, then doing sampling on this node would really takes a long time and would becomes a problem. So in other words, I think TGAT also did an experiment which samples the events based on their how long did they happen. So if it happens very old, then it has less probability of being sampled. But I think their conclusion is that this sampler is too expensive, and it also doesn't boost the performance a lot. So actually, it doesn't even boost the performance. So I think I think if you're looking to a very, very highly skewed graph where you have some very high degree nodes, probably a node memory based TGNs with a most recent sampler, with a most recent neighbor sampler would give you the best performance.
Yeah, I'm imagining like let's say we're in an account abuse team. Like sometimes you might see a bot that is like periodic and it's just like a heartbeat. Other times you might see it's like a sock puppet that was planted a year ago, and then it's kind of dormant until it gets activated. And so it's just they're interesting patterns. And one more question here is, again, this is more just like tactical or whatever. It looked like in the model here, you're looking in not necessarily your models, but the models that seem to be happening here. And also for the data representation on the TGL side, it seems to be that essentially that the events are edges. While we actually see in a lot of our graph modeling work, it's more of a hypergraph where events are nodes. And so if there's like an event involving multiple entities, the event would be linked to, you'd have like that event node hitting multiple. Now, I was curious if you could, any comments about just the data representation.
Yeah, so in the if your event is a node, I think you can also use a similar data representation, which basically sort the node events that are happening at one edge. So, or in other words, you can put a special indices here that denotes there is no it's not an edge, but it's just a node. And I think the reason why we only show the examples with edge events is that it's very hard for us to find an open source dataset that contains node type events. However, these models, I think most of these 5 models or the other TGN models, they can be easily adapted to support other type of node events.
Wait, so I was unclear. So for in TGL, you can support both models, or it's like in theory you can support it?
You can say it in theory because I haven't write any code for that. So right now it doesn't support that. But in theory, it's not very difficult to support that. You can basically modify this TCSR data structure, where instead of these destination nodes you're recording here, you can just record your say your node event ID, and this CSR will basically store your the event that happens or that is related to this node. So it won't create problem. It still should work under the current framework, but I haven't
actually, I didn't realize is a badly formed question, because in those hypergraphs generally you could duplicate the node's timestamp on its outgoing edges anyway, and so you just duplicate the timestamp anyway. So it's you could just use this directly, I guess. So it's
yes.
All right, thank you.
Leo, this is Tristan from NVIDIA, because you mentioned about cuGraph. I wonder, like, what kind of sampling are you guys did you use in your project? Are you using like any GNN frameworks?
Yeah, we're focusing on DGL through PyTorch, but yeah, this is just like a variety of like machine data and social data, basically, and then a little bit of business data.
Right, because recently, like the DGL.8, they introduced a UVA called a virtual address thing. We test like have performance improvement on multiple models. I wonder, have you tried that?
No, I think we're on like 6 or 6 or 7.
I test my personally, like RGCN, GraphSage shows 3 times, 5 times. And I also have a good scalability from 1 GPU to multi GPUs. Check UVA samples on DGL 8, I believe it's 0.8. You can find more information on that.
All right, the UVA, awesome, thank you.
Yeah.
Actually, maybe Tristan, if while we're here, like something we were also thinking about that is like if we actually have shared memory between the CPU and GPU for some of these. Like I know sorry. Like I think there are certain like allocation modes like nowadays where you can kind of do a bit of like some form of like sharing here. I'm wondering if there's anything going on here to be thinking about.
So the data loader is actually using the shared memory anyway.
Alright,
it's actually multi-process, which is like we found a couple of issues before actually release. Yes, it's the data loader is multi-process, while the UVA is actually to just like using pinned memory. We call zero copy from the CPU to the GPU.
They pin memory, yes. Yeah.
They do use the shared memory for data loader.
So actually, I have a question on this. So I wonder that for the super large scale data set where it cannot be where it cannot fit in the main memory, I read from the news that NVIDIA is currently doing some direct reading from NVMe SSDs. I wonder if any like graph framework would support that.
Because I honestly I'm not in that loop. I know someone's doing that. Probably Graph team. I can, if you want more details, I can make sure that you have the right connection for sure.
Yeah, because I see that in the demo, like with the PCIe 5 or PCIe 4, if that's with that NVMe SSDs, they can achieve like similar or even faster sustained performance as copying from the main memory, and that's very appealing, I think.
Yeah, I know someone's doing that, but it's not in our team. I am actually building the GDL team inside NVIDIA, but I know which team is doing that. If you're interested in.
Yeah, when I was mentioning the DAS QDF, like starting I think around the beginning of the year, they have native GPU direct, and so when you're doing like let's say a Parquet read or whatever, if you hooked it up right, it'll just like if you did your OS right, it'll automatically do the GPU direct. Like let's say you're doing from the network or from SSD. And so, but that would not be in your CSR format. So then the question would be, can you also do like an on GPU transform of the CSR? You know, for example, like this is more for the end-to-end GPU.
Great.
Which I think cuGraph has their native CSR transform, but I don't know if
they do.
Yeah.
They show the different format conversion inside cuGraph.
Yeah, so kind of an interesting question could be is if we could get a for the TGL, if you could do like a native, like a GPU native CSR conversion.
Okay, great. I guess well, happy Memorial Day weekend, and thank you all for attending. And we'll see you next month.
Yeah, thank you.
Thank you.
Yeah, thanks everyone.
Bye-bye.
Bye.